in a way, this isn't going to be about my work about trees. Most of that's been with climate downscaling, as described. Some of it, I mean, Dan's going to talk about pests tomorrow, also for our trees focus. So I'm back to really picking up the idea of microclimate modelling. And it's also a shameless plug for this sort of opinion piece, short review article, for which I'm desperate to get Google citations above 0.
Saying that trees worker will also.
So very briefly, I mean, yes, pests are a problem. I mean, they're still estimated to reduce, global crop production by 20%. You only have to look around at forestry in the UK to see us losing all our ash trees. Not just, of course, the actual, biomass loss or the death. It's also, in many cases, the actual cure can be as bad as the actual problem, whether that's excessive pesticide use, particularly when it's not very well targeted or timed, or whether it's felling mature trees and hope the disease doesn't spread on rather dubious evidence. So pest risk modelling, I'm using an extraordinarily broad sense, sort of including some forecasting modelling in that. Short term, just to target treatments more effectively. Longer term, obviously to predict effects of climate change, other factors. And often form part of sort of integrated pest management systems. That's still the term. I'll skip over this, I think, because I think I showed it Dartington anyway. So this is going mostly about project we're doing with Met Office and DEFRA. And also actually a bit of forest research who have joined in, and Kew Gardens. So in a way, this is talking about models of particularly sort of pest growth, survival, reproduction, from which one can then derive some sort of measures of risk. That might be speed of number of generations produced in a year, or whatever it might be. So there's lots of models you might also use, like pest dispersal, host distribution. But probably the most common are those pest growth, survival, reproduction, and a key predictor in nearly all of these models is temperature. They occasionally throw in some others just for good measure, but frankly, it is really a temperature-based model. It's a thermal response, largely because pests cause ectotherms, so they are highly dependent on the temperature or their surrounding conditions. Occasionally, other weather-related predictors thrown in, particularly more of the fungal diseases, such like or slugs. So these I'm going to talk what my critique, or I talked about really, is these slightly biophysical, you can call them, I suppose, models. And they're very much based around the idea of a temperature response model. Different disciplines might call them temperature performance curves. I think there's various other terms for them. And as with a lot of biological responses, they're nearly always non-linear. That's a sort of typical shape of them, and it's sort of gives a sort of biological response to temperature. You can link it back to sort of enzymatic responses to temperature. The actual pest risk models can involve quite a lot of these. Different stages in a life cycle might involve different types of thermal response, but they all tend to be pretty simple, really, as models go. They tend just to be sort of linked together, and they tend to be, as I say, just an accumulation of thermal response. So you might think, well, what could possibly go wrong? It's pretty simple. There's only so much can go wrong. The trouble is, in a way, no one's often. One of the problems, of course, no one tends to look. I've got off a bit. It's not really hampered by a dearth of published information about the causes. It's simply hampered by a dearth of any publications about the success of models. I'm not saying this is unique in any way to sort of test models, but yeah, it's a problem. Occasionally, that's one of the advantages, of course, being a university researcher, you're often very distant from anyone who has to use your models. If you can't sort of, in a way, pretend they are working, the question then becomes who, if you like, what to blame for model failure. As we just focus on these sort of thermal response type pest models, it's quite interesting when you look at the literature and you have sort of entirely separate debates going on, almost in parallel, and only really sort of recently have they really been sort of joined together more. So some people might blame the whole theory of a thermal response curve, some might blame the modelers, the developing modelers, for not in way developing them rightly, and a lot of people blame the users using the wrong kind of data to actually drive models. So this critique of the concept of thermal response, and it's mostly around the plasticity of an organism's response. And this might be sort of genetic, might be variation between populations of the same species. It might be due to some environmental exposure. It might be due to some genetic genes. It's a valid point. I think overall the opinion is nonetheless, there might be variation, but one can normally cope with that. And only in sort of fairly extreme cases is a significant factor, although it does vary a lot. So with aphids, there's been quite a lot of work showing how different populations have quite different responses of the same species. People blame models, yes, of course, and how the response models are developed. And it's interesting, a lot of the debate's actually focused on, so when you're developing your thermal response model, typically you would look at sort of different populations of an insect, say growing over time, developing over time, each kept at different constant temperatures. And from that, you would then fit one of those curves for thermal response. So there's been lots of sort of critique about, is it actually the constant conditions about the problem compared to variable field conditions? It's just sort of missing a point, really, because it's much more really, in a way, it's about microclimate. So under experimental conditions, your constant temperature there is effectively, that is a microclimate, but the experimental insect is exposed to, it's even probably its body temperature as well, because it's constant, not much is happening. As soon as you put in field conditions, though, your variable air temperature is certainly not going to be equivalent of a microclimate in which the pest out there actually lives in, and it's certainly not going to be equivalent to its body temperature. And in a way, a lot of pest biology is sort of doing this leap of faith, if you like. The actual pest risk thermal response curves really just this bit here. It's really a response to insect body temperature and how quickly that affects its growth. So you end up with this leap from using maybe just standard weather data, climatic data, maybe weather station in a field, and you're effectively applying that to models sometimes that aren't really, they're actually really being driven by body temperature, which means you're missing out quite a lot of factors, sort of physical factors actually affecting your microclimate conditions, but then also a lot of biological, ecological factors as well in terms of physiology of pests and how it behaves. So in a way, there's an argument paper that mechanistic microclimate models, are they white knight? They're certainly extremely useful. Thermal response models, I think, are generally valid, but have to be driven by suitable data, which actually describe the conditions in which they live, at the very least, if not their actual body temperatures or an estimate of that. And these aren't simply coupled to weather station data or gridded weather data or whatever or other kinds of climate data. So, a bit of a shock of it, I'm actually going to present some empirical evidence. So look away if it makes you feel queasy. So this is from some work doing with, as I say, Met Office, Kew Gardens, Forest Research, and we've been putting out temperature loggers both beneath the canopy, woodland, and also actually taking bark temperature measures. The reason is we're sort of interested in bark boring pests. So it's a specially designed thermocouple actually we sort of inserted into the bark, different depths, and we have a sort of specialist logger also temperature actually under the canopy. So the left is, so we looked at different depths, north and south facing aspects of the tree trunk. So on the left, blue are two different loggers at different depths on the north side, and right hand side, so red is again bark temperatures, just below bark temperatures. The black is the actual beneath canopy air temperature. So in a way, that's already a microclimate. I mean, that's already been sort of modeled, but it's not modeled, it's measured. So it's not weather station data. And you can see, okay, maybe the upper temperatures, you see obviously the north side bark temperatures don't really reach the actual beneath canopy air temperature data. South side do, sometimes exceed them, probably where you get the sunlight actually hitting the tree trunk, sort of direct radiation, perhaps increasing that. The biggest difference you see is particularly in the way at night, we have a great deal of buffering of the temperature beneath in the bark. And this is just talking about, several degrees, often certainly throughout the summer, 2-3 degrees you can get. So these are sort of the actual log, not modelled temperatures. So I just very quickly sort of been looking at if you apply this to a bark boring beetle, in this case Ips topographus, which is killing particularly Norway spruce trees all the way across Europe. Quite serious forest damage throughout. Lives just below bark, mostly overwinters as an adult. It can produce typically 1, 2, sometimes even 3 generations in a single summer, spring, summer season. So that's quite a lot. And this is just, so this is, we model sort of 2 successive generations. First, each sort of 3 stages just modelled. So it's sort of the emerging adult right at the start of the year. That takes ages because it's too cold and it doesn't come out too quite late. Then when the adults flying around laying eggs, and then the actual sort of egg to adult development, which is the sort of the reds and the pink there. So if you sort of drove these models just using beneath canopy air temperature, you get 1 generation sort of maturing, but certainly by September, looking at results, probably even by the end of September, the 2nd generation has failed to actually sort of reach adulthood, which means it won't overwinter. It'll probably be killed off in the wood if they don't reach adulthood. So even just between these microclimates, actually looking at the sort of bark temperatures rather than the air temperatures, you have quite significant effects on the actual risks, or it's presented by some of these pests potentially. That's strange, all fonts are different, there you go. Anyway, so I guess in the paper is argue that it's actually not just a useful predictive tool in terms of driving these models, perhaps improving reliability of models by using more appropriate weather data. But it's also quite a useful explanatory tool. So needless to say, actually directly measuring microclimate at scale is pretty impossible, more impossible for future conditions. So but we do need microclimate data and mechanistic models of the kind it is developed very much sort of offer a way forward here. Not just to say increase predictive power, but also better understand causes of model failure. Yeah, I don't know if I was going to take that one now. I don't know if it's worth emulating, shall we say, all this, this series of models, if you say, which connect in a way the sort of climate, the actual body temperature of the organism. But certainly, I think mechanism models can help us find out. There may be conditions where it's perfectly okay to make that leap of faith, right? But others not. Anyway, a question when you start have the ability of mechanistic microclimate models now, not so much can we model something, but what we decide to model, and it gets actually quite complex there. So we can use them to explore in a way the effects of different parameters, sensitivity to different parameters. And this can be done in various highly sophisticated ways, I suspect, or some more naive ways. Sort of thinking of just modelling a hypothetical landscape, different canopy covers, or different leaf area index, for example, to see then how that affects sort of the outcome of pest risk models. But I think when you actually start using microclimate models, it also raises the question of what microclimates we want to actually model, which microclimates are actually available. For example, with Ips, it has appeared in the UK, it's not yet established, but where it appeared tended to be in wind-thrown areas of woodland. So you could argue that perhaps it appears there because the trees are more vulnerable, because they've been damaged. But I think it's as likely because the wind flow has actually created new microclimates, perhaps more favourable to the pest. So once you obviously open up a canopy, once you perhaps have fallen trees where the trunk is much more exposed to radiation, then they become much more favourable habitats for a lot of these pests. So it sort of raises the question, should we be modelling perhaps these extreme opportunities for pests to arrive? Should we be modelling mean conditions across the canopy? Should we be thinking about populations of individual pests? And it also sort of raises the question of how microclimates are used and modified by a pest. pests are rarely evenly, they tend to be distributed often through a trunk. There are actually some pests, there's an example, I think one of the wood borers, it's mostly found on the north side of a trunk because it tends not to actually like high temperature. Sort of optimal temperature is actually quite low. And it's also a question about how dynamic the pest response is. Obviously, some pests aren't very mobile, probably won't be an issue. But once you start getting these dynamic responses, how much do pests actually seek out, if you like, an optimal microclimate within the range of habitat you can actually occupy? So in the way the question I say, it's not really the way can we model, it's what and how we use microclimate models in terms of the application to pest risk. So one way, DEFRA is quite keen to sort of use sort of in a way some sort of emulation of this. So we're sort of looking at contrasting scenarios, if you like, of favourability. So choosing sets of parameters that might, so if you say, sort of generate particularly warm microclimates, so then sets conditions for produce sort of particularly cool conditions. Just almost get a range of possible risk bands, however you wish to put it. But I think the main point is, I guess as an ecologist a long time ago, which I quite like about the use of microclimate data, mechanistic modelling, sort of refocus the attention on the ecology of the plant pests. Because in a way, when you're just using weather data to drive some of these models, that sort of almost doesn't matter where the pest lives, because you're just using weather data. When you actually accept that the conditions the pests are exposed to is actually what's perhaps most important, then it's actually the ecology of pests becomes much more key. Yeah, thanks to those people. I'm going to leave it there. So get to a bar.